All right, welcome to the first lecture for Math 272. I guess I'm your new instructor because you did not have me last semester, but hopefully you find these videos somewhat interesting. Basically what we're going to be thinking about with these videos is I'm going to give you a bit of a guided reading. Sometimes with these flipped classrooms you can be asked to only read the textbook and then show up to class having read the textbook and not really knowing too much because math is hard to read. I completely agree with all of you on that. So that's kind of the idea here is that we're gonna read, but we're gonna do it in a guided way, and I'm really gonna point out the more important parts to each chapter and each section, so that it makes a little bit more sense what we're trying to pay attention to here. So this is part 4. I assume you made your way through part 3, 1 to part 3 just fine. We're looking at calculus in higher dimensions. So this is kind of our version of Calc 3, so to speak, and you've done some linear algebra, so you understand what higher dimensions is like. We're going to move our way into really functions on these higher dimensions, and these functions have very special names. Okay, some of these functions we like to call curves, some of these functions we like to call scalar fields, some of these functions we like to call vector fields. They all kind of have slightly different meanings based on this. Okay, what do these symbols mean here? These R to R3, R3 to R, and R3 to R3, so forth. What these symbols are meaning is that it's saying gamma here, it's a Greek lowercase gamma, it's been bold-faced. Here's something to note. The author has bold-faced all vectors. Also, we've put, the authors put the little vector symbol above it as well. So that's one way to figure out what it means by vectors. Why is this one in particular a vector? Gamma by itself really isn't quite a vector, but what it's saying is that at the very least, where is gamma sending things? You can think of gamma as a function of one variable, often t. It takes in a variable in R, takes in a real variable, and it outputs a vector in R3. So this maybe you call it gamma 1, gamma 2, gamma 3. Okay, that's sitting in R3. So that's why they're calling it a vector, is really because of the output of gamma is a vector. The input is not. Now, what do they call those? Right, what are we talking about here? This one is the example of our curve. The next one is the example of our scalar field. And why do they call this a scalar field? Well, anytime you see the word field, in physics in particular, the physicists really like to use this word, field, more or less, is any function with a vector input. So a field you can think of as any function with a vector input, but the reason why it's called a field is that the idea is that maybe we're sitting in some higher dimensional space, and the function takes every point. This would be like R3, right? The function takes each point in R3 and assigns it something. Okay, so it takes maybe that point, and in this case R, it assigns it a number, call it 7. It takes this point and assigns it a number, call it -3. It takes that point and it assigns it a number 14. It takes that point and assigns it a number 2. Every single point in R3 has been assigned a number by this function f, and the idea is that the collection of all these numbers as they get filled up, as the entire space gets assigned a number, the collection of all those numbers forms a field. The idea is like if you were to go out to a farm and plant some wheat, every little seed that falls into the ground sprouts a height of an amount of wheat, and that height is like a number that's been assigned to that point on the ground. So that's where the term field originally came from, and that's really what it's talking about. It's called scalar. Let's talk about scalar in particular. Scalar field, since R, the output, is a scalar. Okay, so that's why we call it a field. We call it field because of the input. The input's a vector. We call it scalar because of the output. The output is a scalar. Now this last setting, the input is a vector, the output is a vector, and hence we call it a vector input field. So in the third case is where we have a vector field, V. Okay, so that's kind of an introduction to those names. Let's talk about really just this point X. So the author is referring to a boldface X with a vector arrow over it. So this is our notation for vectors we want to think about. It's really just a collection of 3 points, right? You saw this in your linear algebra chapter, but this is something new, okay? X times X hat, Y times Y hat, Z times Z hat. Maybe you did see this. I wasn't in your course last semester. But what's going on here is that these, you'll recall from linear algebra, all spaces have bases. Yes, I rhymed on purpose. This is the base. Cis for R3, in the sense that we assign X hat, we define it to be 1, 0, 0, we define Y hat, Y hat is defined to be 0, 1, 0, we define Z hat to be 0, 0, 1. So that's what this notation is trying to get at, is saying you can take scalars, I can take the scalars lowercase or unbold X, unbold Y, unbold Z, those are all in R, the real numbers, and I can scale each of these special vectors by an amount, and that gives me an arbitrary vector in R3. Okay, so I had called these vectors gamma curves. These are curves, and we can think about them with a single input and 3 outputs, as I said earlier. In those curves, we can be a little bit more specific about how they look. More generally, right, we can have a curve take input values from a restricted domain, and the output can lie in an arbitrary dimension. So really, we can talk about any one-dimensional input and a higher dimensional output. It can actually even be one-dimensional, but any one-dimensional input to any number of outputs is called a curve. A planar curve, right, this is a very specific example, but planar means it ends up in the plane, right? That's this idea of planar, ends up in the plane. The plane is R2. Anytime you see plane, you should think of a 2-dimensional space. So here's an example of a nice curve. This is the trefoil knot. You can look at it a little longer if you want to, but I'm going to move on. Scalar fields we have over here. It's possible that the input, right, so I originally said it's R3 to R, but really the input can be anything that's defined to be some dimensional space, right, or a manifold even. For example, over here you still have a scalar field. It's understood here that this is some manifold, and actually over here the 0 to infinity kind of, every time we see 0 to infinity we should think t, it evolves over time. Okay, so we can actually have a scalar field which also depends on time. You can either think about that as a 4-dimensional space scalar field, like space-time scalar field, or you can think about it as a 3-dimensional scalar field. It assigns a scalar to every place in 3 dimensions, but those scalars happen to evolve over time. It's up to you how you want to think about that. Okay, so this is kind of what we're talking about here, is that it's the kind of the best way of representing higher dimensional functions. We of course can't exceed. We can't exceed 3D for obvious reasons. Hence, plotting, we have f from R2 to R is the best we can do. Okay, because the R2, this is our length and width. This is in that direction and that direction. Maybe I'll say that over here a little better. R2 is like that direction and that direction. This forms R2. And finally, the image direction, we'll do in yellow. This is R. And that's where we're stuck with R2 to R. It's kind of the best we have for plotting. We don't have too many other good ways of plotting stuff. So unfortunately, we're kind of restricted if we want to think visually about these things. And thankfully, algebra can save us. Okay, and then here's our vector fields, which I already talked a little bit about, but let's move on to an example of a vector field. This, for example, is actually a vector field which is mapping R2, because we're sitting in a plane, so it's a planar vector field, And that tells you where, this tells you the field, recall, and then this tells me the dimension of the vectors which are assigned in that field. And you can tell here that these vectors have 2 dimensions because they have both a left-right direction and a up-down direction. So this is an R2 to R2 vector field. It's a nice example of one. So we can wrap this up in a quick example. Curves are trajectories of single particles. Right? If I want to graph a single particle, I'm going to call that a curve. That's like this one, for example, right? The path of one particle, maybe I can trace it out with my little, here we go. Maybe one particle is traveling around this curve, like that. There's my one particle. That's a curve. If we go here, scalars describe quantities of fluids, pressure, temperature, height. So if we go over here, we have a fluid in 2 directions, right? 2 dimensions. And then it has a specific height at each place, and that's given by the up-down direction. And then finally, vectors show the whole group flow, right? So we have one extra piece here in the vector. We can maybe think about if this is a vector field describing the flow of a fluid. If I drop a little, maybe I'll make it yellow because I'm going to draw myself a little rubber ducky. I dropped a little rubber ducky sitting on the sitting in this vector field. What's its flow going to look like? Well, it's going to be flowing, and then it's going to go really fast and then flow all the way back around. And so vector fields really describe the flow of an entire field, rather than some quantity, which is what a scalar field describes. Okay, let's move on to the next section. So the next section is curves in space. So we're only going to look at curves here. How do we actually deal with these objects in a mathematical fashion? Well, let's recall this definition, and we see an R right there, which means that it takes a one-dimensional real input. That's what we're going to think right there. And oftentimes we like to think about these as time. This one-dimensional real input we want to think about as time. So a curve takes time as an input. And of course it maps us to three outputs in R3. It's just any function that's defined on those 3. Now we can think about it, right? Physically, what is that representing? Well, the first output is representing the x position of this curve at a specific time. The second output is representing the y position of a curve at that time, and then the third is the z position of that curve at a time. So let's look at a nice example here. Here is gamma equals tt. How do we want to think about this? Well, it's telling me that at time t, x value is t. And it's telling me at time t, the y value is t. Before I jump down a little bit, I want you to think, what should this look like if the x value moves equally to the y value with time? They're both exactly equal to time. All right, we're going to jump down and we're going to see if you're right. So what we can see here is we have exactly a line. And more importantly, this is the line of slope 1. So we gain exactly a line, and that's because the x value, right, at each point in time, maybe t equals 0.5, it says the x value is 0.5, but also at t equals 0.5, it says the y value is 0.5. And so both of those end up at this point, and we know that starting there, it took us 0.5 seconds, or whatever our unit is, to move up here. And then if we do it again, 0.75 seconds, we've moved up there. 1 second, we moved up there. Now, of course, you can get much more complicated than that. If these were the only functions that we were graphing as curves, there's no reason we would do it. But it turns out that plotting even 2-dimensional graphs as curves is extremely useful. Okay, so the nice thing about curves is that we can actually take derivatives of curves as well. And the way we do it is exactly as one would expect, but we have to be careful because our derivative definition is dealing with vectors. Okay, so the derivative looks the exact same. This is the limit of the difference quotient. Same derivative we've always had from Calculus 1, but we have vectors everywhere. So the way we want to interpret this is actually as gamma dot t1, gamma dot t2, gamma dot t3. The 3 vectors of gamma are each calculated by their own difference quotients. This is gamma 1 t plus delta t minus gamma 1 t all over delta t, and so on. So they all get calculated with their own difference quotients. And that's just because of the way that scalars and limits interact with vectors. They are equivalent, but this is how we want to think about them. We're going to calculate these element-wise. So let's scroll down just a little bit. And it's showing us exactly what I was just saying. We're just going to define those element-wise, which makes your life very easy. But let's think about this function then. So it's calling this the graph of a quadratic function. So I'm thinking something like y equals x squared. But then I see this. I'm going to ask myself, why is that curve equivalent to y equals x squared? Well, let's talk about it. Let's talk about why those are equivalent. If I look at this entry, that entry says x as it evolves over time equals t. And the second entry says y as it evolves over time equals t squared. But if I invert my interpretation of this equality, x of t equals t, if I invert that and think about that equality actually as being t of x equals x, and really I can just think about that as t equals x, then down here I see that y of t is t squared, which gives me that y of x is x squared. And so we exactly recover y equals x squared with a curve like this. And so it's not quite clear why that would be the case right away, but we're going to get more and more used to it, that this is how the curve is going to look. All right, so let's scroll down. Let's look at the curve. There it is. There's our beautiful parabola. Let's talk about taking a derivative of this curve. If I take a derivative of this curve, based on what I know, I'm just going to take a derivative element-wise in t, and that's going to give me 1 and 2t. Now, this is kind of cool because this derivative is going to be dx dt and dy dt. And suppose, remember we're starting out with this function, y of x equals x squared. Suppose I wanted to extract y prime of x. Well, I already know that that's 2x, but suppose I didn't know that. Suppose I didn't know it was 2x. What I know is that y prime of x is dy over dx, which happens to be dy dt over dx dt. And I know what those are, because dy dt is 2t and dx dt is 1. So I recover 2t over 1, I recover 2t. But how can I write t in terms of x? Write t in terms of x right there, because t is x. So this is actually 2x. And we recover exactly the derivative that we're very much used to. But suppose I want to stay just in terms of t. We can take a derivative, and there you go. We have our derivative 1, 2t. I like this include better visualization of tangent vectors part. I'm not going to do that, but I guess that's something we can do if we want to. All right, this is a cool example. This is the circle curve. So one might be a little surprised as to why the curve gamma of t equals cosine 2 pi t and sine 2 pi t for the x and y coordinates gives a circle, but I'll explain that right now. If I have x, which is cosine, and I have y, which is sine, and I also have my circle equation. Does everybody remember their circle equation? It's not a big deal if you don't. This is kind of the unit circle equation. Well, we can look at what is x of t squared plus y of t squared. That's just going to be cosine squared plus sine squared, which we know by Pythagoras is 1. And so we actually do recover the unit circle because we have x squared plus y squared equals 1. So that's where you can extract that this is the circle equation for a curve. You can find the tangent vector just by taking derivatives element-wise. We're going to get minus 2 pi sine 2t for x, minus 2 pi cosine 2 pi t for y. And we can look at the graphs here. So there's our unit circle on both. And what's actually being plotted is this is the tangent vector that we've extracted with gamma. So the tangent vector, by taking a derivative with gamma, is we're recovering the full. This is telling me that at, what is this? This is at t equals 0. My tangent vector at t equals 0 is negative 2 pi sine at 0, 0. 2 pi cosine at 0 is 2 pi. That's saying that the tangent vector is a purely vertical vector, right? And I can do similar things at t equals, looks like that's at 1/8 maybe. If I plotted t equals 1/8, I would recover up here at t equals 1/8. I'd recover negative, I guess, 2 pi over root 2, and I would recover 2 pi over root 2 here. Okay, so that means it's equal in magnitude, left and right, or left, right, up, down, but we're going to go left, and up. And that's exactly what we see over here. It's left and up equal in magnitude. So that's why these are useful, right? So we can find tangent vectors really quick to any curve just by calculating derivatives on each part. And of course we can keep going on, right? We can calculate two derivatives element-wise. And there's an exercise there. I'm not going to go through that one. And then there's something very special that happens. Lengths of curves. This is a little fun fact. This is what gives us general relativity. Spell that wrong. You're right. So this is what gives us general relativity. You can calculate the lengths of curves for very abstract objects, and when you do that for those abstract objects, you recover that the shortest possible paths sometimes are not straight lines. So you calculate the minimum length of a curve, and you find out that those are sometimes not straight lines, and that's where all of the gravity from general relativity comes from. Is that actually all of the objects in the universe travel not necessarily in straight lines, but they travel the shortest possible path between 2 points, and that's what general relativity is all about. So we want to know how to do this. The way we do this, I would love to derive this for you, and if you want to see it in class, I'd have a lot of fun doing that. But the way we do this is with the following formula. The length of a curve from the point A to the point B in time, right? These are 2 points in time. So the length of a curve from point A to point B in time is we take the derivative of that curve, and then we calculate the magnitude. This is the magnitude of a vector magnitude. So you calculate the magnitude of the vector, which is the derivative of the curve, and then you integrate that from A to B. We're going to integrate that from A to B. And definitely, if you want to see me derive this in class, ask me, because I really like the derivation. Well, let's calculate that. Let's calculate the circumference of a circle using this idea. So we already know that this curve here is a circle. We can take its derivative really easily. If I compute the magnitude of the derivative, let's compute the magnitude of that. Well, that's the square root of the first entry squared, 4 pi squared sine squared 2 pi t, plus the second entry squared, 4 pi squared cosine 2 pi t. And thanks to our friend Pythagoras, we know that sine squared plus cosine squared is 1. So this is actually just root 4 pi squared, which is really just 2 pi. So that's the magnitude. And we see that's 2 pi. And then if we integrate that over our bounds, the bounds on the circle are 0 to 1. So let's integrate 2 pi over the bound 0 to 1. And everybody knows how to integrate 2 pi over the bound 0 to 1. That's supposed to say 2 pi dt here. Dt. And we just get 2 pi. And what is the radius of the unit circle? Sorry, not the radius. Well, the radius is 1. The circumference, everybody knows, 2 pi r. So this is 2 pi. So actually we could do this for an arbitrary circle of radius r, and we'd get the same formula. So this is really nice that we can now calculate the circumference of a circle for free. All right, that's all I have. I'll see you in class. Bye.